Welcome back to the eLearning Core 3 Fixed Income Analysis, Session 3.2. In the previous session, we introduced duration as a measure of interest rate risk. You might recall that duration is based on an approximation which assumes that bond prices and bond yields have a linear relationship. However, the relationship between bond prices and yields is typically more sloped or convex. Therefore, convexity is a better measure for assessing the impact on bond prices when there are large fluctuations in interest rates. This session consists of two learning goals. The first learning goal is that you understand that duration is only a local risk measure of interest rate sensitivity. This means the assumed linear relationship between bond prices and bond yields is only a good approximation for assessing the impact on bond prices when interest rate fluctuations are small. The second learning goal is that you know how this approximation error can be reduced by considering the in fact convex relationship between bond prices and yields. This convex shape also means that a portion of the interest rate that move remains uncaptured by duration. To obtain a more accurate picture of the sensitivity of a bond's price to changes in interest rates, it is important to consider both duration and convexity. The graph on the left shows the bond price as a function of the yield to maturity for a 30-year bond with an 8% coupon rate. As you can see from the graph, the relationship between the bond price and bond yield is nonlinear and shows some degree of convexity. Duration as a measure of interest rate risk is derived mathematically from the slope of the red tangent line. When you look at the red tangent line, you immediately recognize that duration is only a good approximation for changes in the bond price when yield changes are small. Larger changes result in a pricing error because the bond price function is convex. In other words, we can conclude that duration is a local measure of interest rate sensitivity or simply a linear approximation. The consequences of using such a linear approximation is that it always understates the value of the bond. This means it underestimates the increase in bond prices when the yield falls and overestimates the decline in the bond price when yields rise. Convexity is directly related to the curvature in the price-yield relationship and is greater the stronger this curvature is. So far, we have a pretty good understanding of convexity and why convexity matters in measuring the impact of interest rate changes on bond prices. The question that is left to answer is how convexity is computed. Mathematically, the convexity of a bond equals the second derivative of the price-yield curve divided by the bond price. The formula for the convexity of a bond with a maturity of t years, making annual coupon payments, is given by this equation, where CFT is the cash flow paid to the bondholder at date t. Note that CFT represents either a coupon payment before maturity or final coupon plus par value at maturity date. As illustrated before, convexity allows us to improve the duration approximation for bond price changes. Accounting for convexity, the duration approximation for the percentage change in the bond price caused by a change in the yield to maturity can be modified as follows. Note the first term on the right-hand side of this equation corresponds to the duration rule, while the second term is the modification for convexity. In this context, it is important to note that for a bond with positive convexity, this second term is positive regardless of whether the yield rises or falls. This insight is consistent with the observation made before that duration always underestimates the new value of a bond following a change in yield. So far, we have a good theoretical understanding of convexity. However, a theoretical concept in financial economics is very often best understood when looking at a specific numerical example. Suppose the bond depicted in the figure has a 30-year maturity, an 8% coupon, and currently sells at an initial yield to maturity of 8%. Because the coupon rate equals the yield to maturity, we know that the bond sells at par, which corresponds to a bond price of $1,000. Based on these assumptions, we can compute both modified duration and convexity. The modified duration at the yield to maturity of 8% is 11.26 years, while the bond's convexity is 212.4. I encourage you to use a spreadsheet program like Excel to verify these numbers for yourself. Now let's assume the yield of the bond increases from 8% to 10%, which implies that the bond's price will fall to $811.46, which corresponds to a decline of 18.85%. This number is the exact decline in bond price due to 2% increase in the yield to maturity. However, the duration rule will predict a price decline of 22.52%, which is considerably more than the bond price actually falls. The duration with convexity rule is thus far more accurate and predicts a decrease in the bond price of 18.27%, which is far closer to the exact change in the bond price. Note, in order to use these formulas, you must express interest rate as decimals rather than percentage changes. This means the change in yields from 8% to 10% is represented by 0.02. Let's have a look at the same bond as before, where we know that modified duration of the bond at its initial value is 11.26 years with a convexity of 212.4. However, let's suppose that the change in the bond's yield is smaller, say 0.1%. So if the yield to maturity increases from 8% to 8.1%, the bond price will fall to $988.85, which implies a decline of 1.115%. With accounting for convexity, the duration rule would predict a decline of 1.126%, which is pretty close to the actual price change. When we account for convexity in this example, we get precisely the correct answer. This illustrates the fact that duration is a local measure and quite accurate when changes in yields are small, even without accounting for convexity. The next question to answer is whether convexity is a desirable feature of a bond or not. In general, investors like convexity since bonds with greater curvature gain more in price when yields fall than they lose when yields rise. For example, in the figure, Bond A and B have the same duration at the initial yield. However, Bond A is more convex than Bond B and thus enjoys greater price increases and smaller price decreases when interest rates fluctuate by larger amounts. If interest rates are volatile, this is an attractive asymmetry from the investor's perspective that increases the expected return on the bond, because Bond A will benefit more from interest rate decreases and suffer less from interest rate increases. However, as you might already know, there is no free lunch in financial markets. Since convexity is a desirable feature, investors have to pay higher prices and in turn accept lower yields to maturity on bonds with greater convexity. After having carefully studied session 3.2, please start with the review questions.